Here we are with Lecture 24, 8.5 and 8.6. In 8.5 we will be covering polar equations and graphs. So the first question is, what is the polar coordinate system? Now you're already familiar with the rectangular coordinate system. The rectangular coordinate system is also known as the XY plane or the Cartesian coordinate system. And when we plot points, we use the coordinates x and y. The point is x comma y. With the polar coordinate system, you see that you have a bunch of circles, and instead of x comma y, you have r comma theta. R represents the radius, and theta is the degrees, or radians, of the position of the point. So here, for instance, 3 comma 45 degrees, from the positive x-axis to this point right here, we see that we have a 45-degree angle. So that's the meaning of the second coordinate of the polar coordinate system. That's your theta. So here's your r comma theta. The r is the radius, so that would be how many circles you go from the center. So one circle has a radius of 1, 2 circles has a radius of 2, and 3 circles has a radius of 3, and that's how you get that point right there. So this is just a quick overview here of the polar coordinates versus rectangular system. As you can see, we have a rectangular system and a polar coordinate system side by side with the same graph, but they are going to be written with two different forms of equations. So here you have this straight horizontal line on the xy plane is the equation y equals 2, whereas that exact same line, if you were to graph it in the polar coordinate system, you would have to write it as r equals 1 divided by cosine theta. So it looks a lot more complicated that way, doesn't it? On the circle on the xy plane is x squared plus y squared is equal to 3 squared. And actually this version is the complicated version, because in the polar coordinates plane, it's simply r equals 3, right? So if you have a circle with a radius of 3 in a polar coordinate world, you would just write that as r equals 3. So polar coordinates are a lot more friendly to trig values and circles, conics in general, whereas the xy plane is going to be more friendly to shapes such as lines. So we already talked a little bit about plotting with polar coordinates, but let's do another example. So here we don't see the concentric circles, although that would be the best way to graph, would be to draw concentric circles for yourself so that when you're going outward you can actually find the point more readily. So for you to be able to see this a little more easily, I've gone ahead and drawn the concentric circles. I realize this looks like a flat tire, but hey, for the upper two quadrants at least, it's a little better. So we can see that the point 4 comma 135, we start at the positive x-axis and then we go counterclockwise 135 degrees. That part is very familiar by now. And then we simply count 4 circles out. 1, 2, 3, 4, and that's how we get the point 4 comma 135. Now you can actually also use negative values in the radius position, and of course you could use radians instead of degrees. So let's start with the easier of the two. The radians, pi 6 would be about 30 degrees, actually is equal to 30 degrees. So you see the pi 6th rotation here. But then why is the point over here in the third quadrant instead of in the first quadrant where you might expect it to be? And that is because we are using a negative 3. So let me show you something real quick. Okay, so I've drawn the concentric circles here for the first quadrant, and if we were to go out 3 circles, this would be a radius of 3. Then the point right here is the point that we would say has a radius of positive 3 and then has the pi 6 for theta. So then what we see over here, the negative 3 pi 6, is we're going in the opposite direction. So instead of somebody walking forward 3 steps, this person is walking backwards 3 steps, but it's in the same direction. It's still the pi 6 direction. So a positive value has you go forward towards that angle, and a negative value has you walk backwards away from that same angle. So these 2 points right here are on opposite sides of the line, this one because we have a positive 3, and this one because we have a negative 3. So let's look at another example. In this example, we have a positive radius value, but we have a negative theta, and that's something we're already familiar with, that if we want to go counterclockwise, we would represent, clockwise. Clockwise is represented by a negative theta value. So here we're going clockwise pi halves, so that would be a negative pi halves, and then we're going 2 circles down. And on an axis, it's not so important to see the arcs of the circles. We just go 2 notches down, and that's the point 2 comma negative pi halves. So now let's look at my open math homework 24, number 1. We see we are plotting in the polar coordinate system, and we have the point negative 2 comma 210. So let's first consider, where is the point positive 2, 210? The point positive 2 comma 210, we're going to start by going 210 degrees. So starting at the positive x-axis, we go counterclockwise. This is 90 degrees. Here we have 180 degrees, and if we go 30 degrees beyond 180, we are at 210. So that's 210 degrees. Now we're going to go 2 circles out from the center, 1, 2. So this point right here is the point 2 comma 210. So if we were to go in this direction still, but walk backwards 2 circles, then walking backwards 2 circles will give us the value that we want. So our point here, our answer, we're going to do in blue here. So instead of walking forward 2 circles in the 210 degree direction, we're going to walk backwards 2 circles. And walking backwards those 2 circles is going to place us right here. So there is our 30 degree point. So this point right here actually can be written in a couple different ways. Actually, a good number of different ways. One of the ways that we can write it is the way that we've already just seen it written. But we can also write this exact same point as positive 2 comma 30 degrees. So this is another difference between the xy coordinate system and the polar coordinate system. In the xy coordinate system, there is only one way to write each point. But in the polar coordinate system, there are a number of ways you can write that. And of course, you could add 360 degrees, and you could end up writing this as 2 comma 390. Or you could subtract 360 degrees, and we could write this as 2 comma negative 330. And then, of course, you can add any multiple of coterminal angles onto this value. Or we could use the negative 2 and add values of 360, add multiples of 360, or subtract multiples of 360 to the 210, and we could end up with an infinite number of options here. So there's actually an infinite number of possibilities for how you could write that single point. Very exciting. Now, I realize I just spent 10 minutes talking about all that, but it is a bit of a transition into the world of polar coordinates, so I didn't want to rush too quickly. Hopefully you have a good sense. And now I'm just going to give you some how-tos to get through the rest of the homework. So how do we switch from polar coordinates to rectangular coordinates? And the secret to doing that are these 2 equations here, that x is equal to r cosine theta and y is equal to r sine theta. So for instance, if you have the point 4 comma 135, to get the x value that corresponds to this point, we simply multiply the radius times the cosine of theta. So that would be 4 times cosine of 135 degrees, which would be 4 times negative root 2 over 2, which is equal to negative 2 root 2. And similarly, if we wanted to find the y-coordinate, we would simply multiply the radius value times the sine of theta, so that would be 4 times the sine of 135 degrees, which becomes 2 root 2. And so the rectangular coordinates of the polar point 4, 135 are negative 2 root 2, 2 root 2. So this is actually a pretty simple, straightforward method. Here's another example. We have the point negative 3, pi 6, and we can just multiply the r value times cosine theta, and you can pause this and read this as slowly as you like. It's the exact same process as the previous slide. And then for our third example that we had looked at earlier, here again we can transition this to what we would expect it to be. This is 0, negative 2, right? How do we get that? We multiply the radius value times the cosine of theta. So in the x case, that becomes 2 times cosine of negative pi halves, or 2 times 0 is equal to 0, and then 2 times sine of negative pi halves is 2 times negative 1, or negative 2. So there's your process. Now let's go back then to my open math and look at number 2. So in the case of number 2, we are to convert the point 9, pi 6 to Cartesian coordinates. So how do we do that? We're going to take our x and our y equations that we already had. We had x is equal to r times cosine of theta. And now we replace r with 9. And we replace cosine theta with cosine of pi 6. And similarly, the y equation is y is equal to r sine theta, so 9 times sine of pi 6. And now we use the unit circle values for pi 6. So here are the substitutions from the unit circle. And now we can write our final answer. Here our x value is 9 times the square root of 3 over 2. Notice the directions say to enter exact values. And the y value we're looking for is 9 halves. 4.5 would also be exact, but the other one's written as a fraction, so we might as well write both as a fraction. And then here is the answer from my open math. Now, I already just mentioned this before, but each of these points has alternative forms. So, for instance, the point 5, negative 110 degrees. If you add multiples of 360 or subtract multiples of 360 from negative 110, then you end up with coterminal angles. So any of the coterminal angles are valid with a positive radius of 5. And then if you want to switch to negative 5, then you can just add or subtract 180 degrees from this original value. And then once you get that first point, you can add multiples of 360 onto this second angle, or sorry, on the second coordinate, which is the angle. So you can review that as slowly as you need to by pausing the video. And now we want to consider how do we switch from rectangular coordinates back to polar coordinates. And there are 2 ways that we want to do that. And one is to remember that this relationship holds. This is a lot like the Pythagorean theorem. And then also that the tangent of theta is equal to y over x. So here we have this rectangular point, and we need to switch it to polar. So in the fourth quadrant, so since that is in the fourth quadrant, when we write the equation tangent theta is equal to y over x, and we end up with a value, when we take the arc tangent, or we look at the unit circle and we try to look for a value, we need to make sure the value is actually in the fourth quadrant. You can also use the negative value. So if you were to use the value negative 60 degrees, this is also in the fourth quadrant, and we are not restricted to using just positive values between 0 and 360, although that is a typical default choice. Now let's look at how to find the r value. The r value is found using this other formula right here, that r squared is equal to x squared plus y squared, so if you were to take the square root of both sides, you can have a positive r value or a negative r value, but since we are aiming for the fourth quadrant, we need to use the positive r value unless we wanted to switch the theta value, which I don't really want to do. So r is equal to 6 squared plus negative 6 root 3 squared, which when you simplify that gives you 12. So you could use positive 12 and 300 degrees. You could likewise, as I had already said, you could use positive 12 with negative 30 degrees. That's completely acceptable as well. And then if you wanted to use a negative r value, you can, but make sure that these two values for your theta are 180 degrees apart from each other. So that is another option. So that's why it says other answers are possible. Okay, so now let's go to my open math again and look at number 3. So in question number 3, we have these Cartesian coordinates and we need to change them to polar. So we want exact values. Let's start with observing that we are in the third quadrant, and we're going to say that the tangent of theta is equal to y over x. Of course, that reduces very nicely to a positive 1. And in the third quadrant, we do have an angle with a tangent value of 1, both in the first quadrant and in the third quadrant, the 45-degree angle and also the 225-degree angle. Both of these have a tangent value of 1. So since we are in the third quadrant, we are going to be selecting the 225-degree angle, unless we wanted to use a negative radius. Okay, for the radius, we are going to use the formula that r is equal to the square root of x squared plus y squared. When you square each of these values, of course, you get the same result, and that would be 50 over 4, which would then give us the square root of 100 over 4, and both of these numbers are conveniently perfect squares in this case, and if they're not, you just give them in simplified radical form. Here we have 10 over 2, and that would be 5. So the best answer, the most straightforward answer is 5, 225 degrees, except that I just noticed something, the directions. In this particular problem, the directions do require that we use a positive radius, which I have done, so check. But then this other part of the directions I did not follow. So it's good that I deviated so that you could be reminded that in this case there is actually only one correct answer, and that is because the directions are restrictive. So we're going to change 225 to 5/4. So then our answer is actually 5, 5 pi-4. That's what I meant to say. 5 pi-4. And there is your exact value written in the correct format. And here you see my open math has its value right here. Okay, so going back to the PowerPoint, now we want to say how do we rewrite Cartesian equations as polar equations, and we're going to use these same equations we were already looking at before, these identities. So let's try it with this one right here. We're going to find the polar equation of a simple line from algebra. So what we want to do is we want to replace x and replace y using these two equations right here. Okay, so that was a pretty painless substitution. Replaced y with r sine theta, replaced x with r cosine theta, and now what you want to do is you want to solve for r. When you're dealing with an xy equation, you solve for y. When you're trying to get an equation, you generally get y by itself. But with polar equation, you're going to want to solve for r. So this is what it would look like. So first we want to put the r terms on one side and the non-r terms on the other side. Then we want to factor out the r. This is just a simple case of solving for a specified variable. And then we want to divide both sides by whatever number or expression is in front of the r. The coefficient of r is 2 cosine theta minus sine theta. So that means that my final result is r is equal to 4 divided by 2 cosine theta minus sine theta. It looks complicated, but the procedure is not that bad. Okay, great. Now let's look at graphing that equation. This equation right here, when we graph it, it's a lot easier to graph this one using the x and y intercepts from Algebra 1 that we learned. And you can still use the polar coordinate system because you have the intercepts intact. These two equations are the same equations. One is written using rectangular coordinates and one is using polar coordinates. Let's look at another example. Here, this one's simple because we already know that x squared plus y squared is equal to r squared. So we can just replace x squared plus y squared with r squared. And then when you take the square root of both sides, you end up, sorry, that's supposed to be 25. You end up with r is equal to plus or minus 5, right? And so either one of those equations is the correct answer. You can write it as r equals positive 5 or r equals negative 5. Typically we use the positive if we had to choose. So then let's look at the graphs. Here you have whether you write it as r equals positive 5 or r equals negative 5. Either way, it's a circle with radius of 5. Now let's look at my open math, number 7. We want to rewrite the Cartesian equation y equals 3x squared as a polar equation. So the first thing we want to do is we want to replace x and y as we did in the problem that we did back here. We replaced x and y with these values here. So we're going to replace x and y. Y gets replaced with r sine theta. And x gets replaced with r squared cosine squared theta, which is the square of r cosine theta. So I really should have written it this way first. I'm squaring r cosine theta, and that results in r squared cosine squared theta. Okay, so now what do? Now remember that our goal is to get r all by itself. What I want to do is divide both sides by a variable if that variable could ever equal 0. But in this case, r is not going to equal 0. The radius is not going to equal 0. So that means that we can divide both sides by r, which is convenient because that's going to eliminate one of our r's, and then for our other r we'll end up with r squared over r, which would then eliminate this squared. So now on the right hand side we simply have 3r cosine squared theta, and on the left hand side all we have left is sine theta. So what's nice here is now we can get r by itself by dividing both sides by 3 cosine squared theta. So r then is equal to sine theta over 3 cosine squared theta. So next I want to show you how to graph, and I'm going to show you page 395, number 47. So in order to graph a polar equation, what I want to do is I want to make a theta r table, sort of like an xy table. The values that I'm going to plug in are all the values on the unit circle from 0 all the way back to 360 without including 360, because that would be the same as 0 degrees. So I've started the table right here, and then I'm going to continue by adding a second copy of the table because you see I've ran out of room when I got to 135 degrees. So next what I want to do is I want to fill in the r side. The theta side is filled in with all the values from the unit circle. So when I replace 0 degrees here for theta, the cosine of 0 is 1. 1 times 2 plus 2 is going to be 4. Cosine of 30 degrees is the square root of 3 over 2. So this becomes 2 plus 2 times the square root of 3 over 2, or 2 plus the square root of 3. Then I have 45 degrees, so cosine of 45 degrees is square root of 2 over 2, times 2 is simply square root of 2, plus 2 is 2 plus square root of 2. 60 degrees. Cosine of 60 degrees is 1/2. 1/2 times 2 is 1. 1 plus 2 is 3. Cosine of 90 is 0. So now that you can see what I'm doing, I'm going to go ahead and pause the video and fill in the rest of the values using that same technique I was just explaining. Okay, so now that I've filled in my tables, I need to graph. Now I can see that the smallest value in my R side of the table is 0, and the largest value is 4. So when I graph, I'm going to make sure that I have 4 concentric circles. So I'm starting off with an XY plane, and then I have 4 notches on each axis in the positive and negative direction, and now I'm going to draw circles through those notches. Okay, now I have to plot each one of these points. So the first one is 0 degrees 4. So starting at 0 degrees, I need a dot at 4. That one's pretty easy. This next one's a little harder. Square root of 3 is about 1.7. So this is about 3.7. So at 30 degrees, I want to put a dot at about 3.7. Then at 45 degrees, square root of 2 is about 1.4, so this is about 3.4. So at 45 degrees, I need a dot at 3.4. At 60 degrees, I need a dot at 3. At 90 degrees, a dot at 2. At 120 degrees, a dot at 1. At 135 degrees, this is 2 minus 1.4 roughly, so that would be 0.6. And then 2 minus 1.7 is about is about 0.3. And then at 180, I'm down to 0. And now I am seeing the symmetry that all of the values here are going to be symmetrical to these values. And when I connect the dots, I end up with a nice heart. So that is how you graph using polar coordinates. Let's take a look at my open math. By the way, that heart that I just drew, the technical name for it in math is the cardioid. What you're going to be doing for questions 8 and 9 is you're not going to be scoring points for these. These are 0 points possible, but this will give you an opportunity to graph without having to do all the hard labor that I just did. So as you move from 0 to pi, you'll get to see what the points would look like if you were to plug points into the equation 5 times sine of theta. And so this is a really cool thing. You can go back and forth and see basically the same as plotting points, but a lot faster. But I still wanted you to know where these values were coming from. And so it's still a really worthwhile experience to plot equations by hand, but we didn't get to have a lot of time for polar equations, so I didn't want to demand too much from you there. you could explore the same for sine and cosine. And by exploring these two, you should get a different sense for how the sine graphs look versus how the cosine graphs look. And that should help you then with doing some matching of different types of equations with their graphs. Okay, and then drawing one by hand, also you can figure out how to do question 11 based off question number 8. But also, if you need help with question 11, you can see example 4 on page 389. Okay, so next we want to learn how to rewrite polar equations as Cartesian equations. So here is a polar equation, and we want to rewrite this as a Cartesian or a rectangular equation. So what I want to do is I want to start by cross multiplying, and when I do that I end up with r times 1 minus cosine theta is equal to 1. So I just got that by cross multiplying. And I was about to just write out the whole thing for you by hand, but it occurred to me that when I set up this slideshow, I conveniently have it typed up for you. So this is what happens when you multiply both sides by 1 minus cosine theta. You get this. And here's the distributive property now. And since r is equal to the square root of x squared plus y squared and x is equal to r cosine theta, you can replace any occurrence of r with the square root of x squared plus y squared, and you can replace any occurrence of r cosine theta with x. So that's very nice. Now we have a square root though, so we need to get the square root all by itself, and then we need to square both sides so we can get rid of that square root. And when you square both sides, you're going to end up with x squared plus y squared is equal to 1 plus 2x plus x squared, and the x squares on both sides will cancel, giving you y squared is equal to 2x plus 1, and this is actually a parabola on its side. So that's what that would look like. So one of the advantages of the polar coordinate system, it allows you to graph things that in the xy coordinate system you wouldn't be able to graph this because it's not a function. So when you're in polar mode on a calculator, you can actually graph what you cannot graph when you are in your regular xy plane on the calculator. Okay, now let's look at homework 24, number 15 and 16. So number 15, we're going to rewrite the polar equation r is equal to 2 cosine theta. So the trick here is actually to multiply both sides by r. So if you multiply both sides by r, you end up with r squared is equal to 2r cosine theta. And then that's really nice because you can replace any occurrence of r squared with x squared plus y squared. Oops. And you can replace any occurrence of r cosine theta with x. So now we have this format right here, and this would end up being an ellipse, right? So you could rewrite this as an ellipse, right? So all you have to do is get the x's and y's on one side and then complete the square, don't you? So if we were to want to complete the square for x's, we would need to add 1 to both sides. So this would have been 0 over here, so that's why I left it blank. And now I'm adding 1 to this side as well. I don't need to complete the square for y squared. It's already a perfect square. Here this becomes x minus 1 quantity squared. And then we already have the y squared as a perfect squared. Oh, that's not an ellipse. What am I thinking? That's a circle. That's a circle with a center of 1, 0 and a radius of 1. So that's very nice. Oh, they left it like that. Well, I did all that hard work for nothing. Either way, if you want to write it as the other answer, it's good. So I just typed that in, and let's see, do I get it right or wrong? Yay, I got it right. So it turns out if you do rewrite it as a circle in the proper format of a circle, you will still get your problem right. So that's a great review of conics. Okay, number 16. Here we're going to start by cross multiplying. And when you cross multiply, then you get to see that we have r sine theta and r cosine theta, which conveniently get replaced with y and x. So then we can rewrite this as 3y. You can replace the r sine theta with y and the r cosine theta with x, and you get 3y plus 16x is equal to 46. And then divide both sides by 3, get the y all by itself. Basics from Algebra 1, and you end up with y is equal to negative 16/3 x plus 46 over 3. And that is finally the end of the polar coordinates lecture. The next part of this lecture covers 8.6, which is parametrics equations, so look for that lecture next.